In today's class, we will discuss about a new method of solving matrix equation, which is very similar to Gauss elimination method. In fact, a variant of Gauss elimination method, which is called Gauss-Jordan method. And through this method, we will see we can directly diagonalize the matrix and get the solution, and this method has its applicability in finding inverse of a matrix. So, we will see how this method can be applied to solve A x is equal to b, and also how we can get A inverse using this method. First, we start with reduced row echelon form. This is a form of a transformed matrix A, and it is said that a matrix A will get a reduced row echelon form through matrix transformation, and the form is and it is defined by RFA in several computer programs. Also functions RFA is called to get reduced to echelon form of matrix A, and the reduced to echelon form of matrix A will be a matrix of same dimension of A, which is obtained after transforming A by certain matrix operation, and this form will satisfy the following criteria, that the leftmost non-zero element in each row is 1, and the this element is known as pivot. So, there can be zeros, and the first non-zero element coming from the left will be 1, which is the pivot in that particular row. Any column will have at most one pivot, and if a column has a pivot, then the rest of the elements on that column will be 0. For any two columns C1 and C2 that have pivots in respective rows R1 and R2, if pivot of C1 is left to the pivot of C2, then the row R1 will be above of R2. That means, the pivots will be arranged from left hand corner and come towards the right hand corner. In other words, a pivot P1 will be above another pivot P2, and this P1 must be also in the left of P2. So, when we will see the forms, we can verify this. When we will see examples of reduced to echelon form matrix, we can verify these terms. And rows that consists only zeros will be in the bottom of the matrix. So, there can be rows with no pivot with all zeros, because if the pivot or if the 1 does not appear here, all the term there cannot be any other non-zero term, all the other terms will be zeros, and that will be in the bottom of the matrix. So, if we see how does a reduced to echelon form matrix look like. So, these are what is typically called a reduced to echelon matrix. This is a pivot term which comes at the leftmost, which is the leftmost non-zero element of one particular row, and in one column there is only one pivot term and remaining terms are 0 in any other column, and each of the pivot terms which are above the other pivot term row wise should be column wise in left of the other pivot terms. So, they are kind of arranged from left to right, and there can be also zeros in certain rows. Similarly, there can be zeros in certain columns also. Reduced to echelon form matrices are not necessarily square matrices, they can be rectangular matrices also, and those will be the rows or columns with zeros only. And this term echelon actually comes from deployment of troop in an army, how in an army soldiers will be arranged in certain form, it is like in a stepwise form, and this the term echelon came from there. And we also see that an identity matrix is also reduced to echelon form, or if we write a matrix like this 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1, this is an identity matrix. These are the pivot terms which are the comes in the leftmost term of one particular row, and one pivot term which is left to another pivot term must be row wise above the other pivot terms also. So, now Gauss-Jordan method states that a method can be transformed to its a matrix can be transformed to its reduced to echelon form through the following row operations: interchange any two rows, multiply all elements of a row by a non-zero constant, replace a row by a sum of itself and a constant multiplier of other rows, any other row of the matrix. So, these terms, like at least first and third one is very much like the processes we follow in Gauss elimination method. So, through row operations, and the second one is also is probably the last few steps in the back substitution in Gauss elimination method. So, through these steps we can transform a matrix to a reduced to echelon matrix, and the advantage is by that if we can get a reduced to echelon form of a square matrix, it will be an identity matrix. So, we can directly solve the equations from in one step, because it will be only a diagonalized matrix with all coefficients 1. So, the the right hand side vector transformed in that way will give us the actual solution. So, let us will look into that that process in a while. We start with the we look how Gauss-Jordan method can be applied for solution of system of linear equation. We start with the equation 211 minus 460 minus 272 u v w is equal to 5 minus 29, and now we will try to get reduced to echelon form of the left hand side matrix, and through the same step we should get solution of the right hand side matrix. We should get solution which will be in the right hand side column vector. So, the augmented matrix means this matrix augmented with the column vector is a matrix like this, and we will see how we get a reduced to echelon form here. So, that the first non-zero element from left hand side will be 1, and as this is a diagonal triangular matrix, the reduced to echelon form will be a identity matrix. In the same way, we will get the solution which will come in the rightmost column or the augmented part of the matrix. We perform Gauss-Jordan steps on it, which are very similar to Gauss elimination form, and including both forward and backward substitution steps until we get the diagonal form. So, this is the augmented matrix we considered in the last step, and now we do row operations. First we have to follow same steps as Gauss elimination. So, I need to make this the second row first term to be 0, so that the pivot terms remains only. For the first row 2 is the pivot term. So, we multiply first row by 2 and subtract from second row. The transformed second row is second row minus twice into the first row, which gives us 2110 minus 8 minus 2, and the right hand side column becomes minus 2 into 5 minus 12. We perform the next step in which I have to eliminate this term. So, I add first row with the third row. I add first row with the third row and get the transformed third row, which is 2 minus 2 0, 1 plus 7 8, 1 plus 2 3, 5 plus 9 14, 0 8 13. Now, I have to eliminate this term if we follow a Gauss elimination forward substitution forward elimination step. So, I will add the third row with the second row. So, transform third row will be third row plus second row. So, 8 minus 8, 8 plus minus 8 10, 2 plus minus 3 1, 12, 14 plus minus 12 2. So, this we get the third row last element to be 1, which is what we should get also in a reduced to echelon form. So, for third row you do not have to do anything, and as this is the last row, we now should start the backward substitution step. What do we have to do in the backward substitution step? We have to eliminate the minus 2 terms. So, twice of third row should be added to the second row, and second row is equal to second row plus twice of third row. So, 0 minus 8 0, and this becomes minus 8. and now we have to eliminate this one, and the next step we will eliminate the other one. So, first row, third column 1 has to be eliminated, that means third row has to be subtracted from first row and we get this particular form. Now, we have to eliminate this one. So, we have to subtract add 1/8 times of second row from first row, and we go to the next page. So, 1/8 times of second row is added with the first row and we get a diagonal form, but this is not a reduced to echelon form, because the left hand side the first non-zero term coming from the left in any column is not 1. In reduced to echelon form they should be 1. So, we have to, for third row it is 1, but for second row and first row we have to divide them by 2 and by -8, and the steps are like this. The first row divided by 2 gives me 100, which is, now this is close to reduced to echelon form except the second row, and then we divide it by -8 and get 100. So, this the left hand side matrix got a reduced to echelon form, therefore, the augmented matrix or the augmented part of it, the fourth column will give me the solution vector, and we can see the final solution is UVW is equal to 112. This is very similar as a Gauss elimination method, only thing now this is more formalized, as we have to get a reduced to echelon form and we have to do certain matrix operation which is can be interchanging of rows. Interchanging of rows are not done here because we did not get any 0 pivots, but these are certain matrix operation like interchanging of rows, adding or subtracting one row multiplied by a constant from another row, and dividing all elements of one row by a certain number. So, that from the diagonal form, like from this diagonal form, we get to this particular form, because first the first row is divided by 2 and the second row is divided by 8, and in this form as the main matrix A is diagonalized, the right hand side column vector will be directly the solution vector. Now, we know that we have earlier seen that exchanging rows is a permutation matrix multiplication by permutation matrix, and subtracting one row from other is also a matrix multiplication. This step we will see is also like dividing all elements of row by a scalar is also a matrix multiplication step, and we see dividing a row by a constant is also a matrix multiplication operation. For example, if this row has the second for this matrix the second row has to be divided by a term q, we multiply this matrix by 1 by q and 1, and this will be a B1 by q, B2 by q, B3 by q matrix. So, all the steps in a Gauss elimination in a Gauss-Jordan method can be replaced by matrix multiplication step, multiplication by permutation matrix or multiplication by a matrix like this, or multiplication by a subtraction addition matrix. So, the Gauss-Jordan method will yield the reduced to echelon form of a matrix A is M into A, where M is the transformation matrix, that means, it is product of all the transformation matrices including row operation matrix, row division matrix and row permutation matrix, and all the series of operations should be multiplied and we will get this matrix A. So, the Gauss-Jordan method will tell me that as I have an equation A x is equal to b, and now I will write M A x is equal to b, because M A will be the matrix operation applied on A and which will give me the reduced row form of A, and this will give me M B. Then x is equal to M B should be my solution vector. So, the matrix operations which will transform A to reduce to echelon form of A should be done on the right hand side vector B to give me the solution vector x. Now, interestingly, this method can be further applied to identity matrices, and we will see that that gives us the inverse of one particular matrix. Now, let us consider the matrix equation A x is equal to b. Solution to this equation will be x is equal to A inverse b, and or if I multiply identity matrix I with x, I x is equal to A inverse b is the solution of the matrix, where I is the identity matrix. A Gauss-Jordan step on x is equal to b will give me m a x is equal to m b, and the solution x will be m b. M is the multiplier of all the matrix operation. So, from here we can relate that the solution is x is equal to m b, and that also tells us that this matrix operation M, when applied over A, gives us an identity matrix I. Therefore, this matrix operation M, when applied over an identity matrix I, should give us A inverse, or from here we can write M A x is equal to M b. Now, M A x and this directly gives us the solution. Therefore, this is equivalent to I x is equal to A inverse b. So, M b can be also written as M into identity matrix into b, and if we compare these two equations, for a square matrix the reduced to echelon form of M A is nothing but the identity matrix I. Therefore, M I should be A inverse, or the Gauss-Jordan steps for one particular matrix A, which will give us the reduced to echelon form of A, or for a square matrix which will give us the identity matrix form of A, identity matrix transformed from A. These Gauss-Jordan steps, when will be applied on an identity matrix, should give us A inverse. A Gauss-Jordan step, after Gauss-Jordan steps, we will get M A is equal to I, or reduced to echelon form of A will get for a square matrix its in identity matrix. Therefore, for if the same Gauss-Jordan steps applied on an identity matrix, M I will give us A inverse. This is a very elegant way of finding A inverse. In a sense, we do not need to go into the intricate process of finding cofactors of minors of each element in one particular row and do a series of determinants calculation and then find out A inverse, which we initially proposed when we are discussing about determinants. Rather, we can see through the processes through which one square matrix can be transformed to an identity matrix, and the same processes will apply to an identity matrix and we will get A inverse, and that is basically a Gauss-Jordan method of finding inverse. We will see it through an example. So, the idea is that we will start with a matrix, A, so that M A is equal to identity matrix. M is a set of matrix operation, or one part when multiply we all the matrix operations operators are multiplied, it is a single matrix which is a matrix operator on A. When we do this set of operations on A, we get identity matrix, and Gauss-Jordan will tell that when we apply the same matrix operation on identity matrix, we should get A inverse. So, we will perform Gauss-Jordan steps on one particular matrix A to transform it to an identity matrix form. We will perform the same steps on matrix I and we will get A inverse. Gauss-Jordan method for finding inverse says, consider the steps in Gauss-Jordan method applied over a full rank matrix A to get its reduced to echelon form or identity form, because it will be same for a full rank square. Full rank matrix is always a square matrix for a square matrix A. If it is not a full rank matrix, then this is a singular matrix and inverse cannot be found. However, so consider a full rank matrix A, square matrix and full rank matrix, apply Gauss-Jordan steps to get its reduced to echelon form, which is identity matrix. These steps, when applied over an identity matrix, will result into the inverse of A. If m into A is equal to I, m into I is equal to A inverse. So, m is a matrix multiplier here, which is basically matrix multiplier of matrix operations or steps of matrix operation. So, different matrix operation step combining exchange of rows, subtracting one row from others, dividing all the elements of one row by one particular scalar, apply on the matrix A and apply the same thing on an identity matrix I. Finally, I will give us I will be transformed to A inverse. And we will see it through the same example. Earlier we solved an Ax is equal to B using Gauss-Jordan step. We will apply now, take the same matrix A and apply Gauss-Jordan steps over it, and same Gauss-Jordan steps we will apply over an identity matrix, and we will see that the inverse is coming out. So, we consider the same matrix A 2 1 1 4 minus 6 0 minus 2 7 2. The augmented matrix, now we are augmenting it with identity matrix, because we want to transform the identity matrix to A inverse also. Same thing with 1 0 0 0 1 0 0 0 1. This 3 by 6 matrix we will try to give it to a reduced to echelon form. So, that the leftmost first element is 1 and the all other terms in that particular column is 0. We will perform Gauss-Jordan steps on it. The right matrix will get an identity form and the left matrix will be transformed to A inverse. So, the first step is that we start with the equation, So, the first step is that we start with that augmented matrix and we do exactly the same steps we have done earlier. The second row is transformed from its second row minus twice of first row. We do the same thing on the identity matrix also. It does not remain an identity matrix anymore, it is transformed. Now, this term has to be eliminated. So, we will add first row with the third row and this is eliminated. Now, this term has to be eliminated. So, we will add second row with the third row and the lowest column got a kind of a reduced to echelon forms, lowest row got similar form 0 0 1. The first non-zero term is 1 here, and this is end of the Gauss elimination forward steps. Now, we will start the backward substitution step in Gauss elimination. So, this has to be eliminated. We will add twice of the third row with the second row, and note that the identity matrix is also getting transformed. Interestingly, it got an lower triangular form in the first row of first set of operation through the forward substitution step. Now, there will be more changes in identity matrix also. So, we go to the step transformed second row is equal to second row plus twice into transformed third row, and this term is eliminated. Now, we have to eliminate this term. So, first row transformed first row will be first row plus minus third row, and now in the identity matrix was a diagonal matrix. Through all this transformation, as we are approaching to a diagonal form of this particular matrix, we are approaching to a diagonal form identity matrix from a diagonal form. Now, it is completely populated with non-zero terms. Well, so now this 1 has to be eliminated. sorry. So, this 1 has to be eliminated, that means this will be multiplied by 1 by 8 and added with the next term. So, there is some mistake here, this will be 0, this will be 0, not this is a this there is a typing mistake here. So, our first row is first row plus 1 by 8th of second row, and now we have to start giving them all the pivots should be 1. So, we divide the second row, all terms in second row by all terms in first row by 2. So, this pivot is 1, and then all terms of second row by 8 minus 8. So, all these terms are 1. So, finally, we get the identity matrix, the right hand side A matrix is transformed to an identity matrix form, and the identity matrix is transformed to a different form, and this is A inverse. So, we will check it, we will multiply this matrix with the initial A and we should get identity here. However, Gauss-Jordan steps tells me that Gauss-Jordan method for finding inverse tells me that once Gauss-Jordan steps are performed over any matrix A, which is a full rank matrix, and the same steps are performed over an identity matrix, the identity matrix transformed to A inverse, or we should say that this is A inverse. So, A is transformed to I and I is transformed to A inverse. Now, let us take this matrix, and to confirm it, take this matrix and multiply with A. So, this matrix is inverse of the original matrix A. So, this is A and this is A inverse as per our Gauss elimination steps. So, let us multiply A inverse with A, it should be an identity matrix. We will practice this multiplication once more. The first term will be the first row first column term will be 2 into 12 by 16, then 1 into 4 by 8 minus 1. So, 12 by 16 plus 4 by 8, right, 12 by 16 into 2 into 12 by 16, 24 by 16 plus 4 by 8 minus 1, which is basically 16 by 16 and 1. And the second term, the first column second row term, that will come as we multiply this particular row with this column. So, 48 by 16 minus 24 by 8 plus 0, 48 by 16 minus 24 by 8 is 0. Similarly, we will multiply the third row third column term here. So, we can probably write it down. So, the first term will be 24 by 16 24 by 16 plus 4 by 8 minus 1. The first row second column term will be then 48 by 16 minus first row second column. So, minus 24 by 8, this will be multiplied with this is multiplied this plus 0, fine. The first row the third row first column term, this multiplied by this will be minus 2 into 12 by 16, which is minus 24 by 16 plus 7 into 4 by 8 plus 28 by 8 and minus 2. So, we will see this is 24 by 16 plus 8 by 16 minus 1, 2 minus 1, this is basically this is 1. This is 48 by 16 minus 24 by 8, which is 0. This is 24 by 16 minus 28 by 8, this is 56 by 16, 32 by 16. So, 2 minus 2 is 0. So, we can similarly go on and find all the terms and you can calculate it, that this becomes an identity matrix 1 0 0 0 0 0 1 0 0 0 1. So, if we can take a large matrix also and perform the same steps and get the same equation, and if we get a 0 pivot, so we have to exchange the rows. For a large matrix, the inverse finding using determinant is much involved, like you have to find out many determinants, find out all the cofactors. For that you have to find out number of determinants, and it will involve lot of steps. Even for a 3 by 3 matrix, you could have imagined that it would not have been that easy. If I go for 4 by 4 matrix, the inverse finding using determinant is also complicated. However, this method is straightforward as it follows a simple logic which is same as Gauss elimination steps. Only at the last step you have to divide each row by one particular constant to get a identity matrix form, and you will end up in getting the inverse of the matrix. And typically for a n into n matrix, the number of steps will be same as Gauss elimination steps, very similar, will be order of n cube, and we can find out that inverse. So, this is one important method of finding inverse of a matrix using direct solution techniques, and it has lot of similarity with Gauss elimination method. We can do a number of practice problems. I will hand you over these problems in your assignment sheet, where you can use Gauss elimination and find inverse, and best thing in finding inverse is that you directly multiply inverse with the right hand side vector and you will find the solution. Okay. So, this is an important step, Gauss-Jordan method, and now we will see in next few classes few other direct solution techniques which are for certain class of methods. These methods is applicable, Gauss elimination and Gauss-Jordan, they are applicable, or LU decomposition, they are applicable for any full rank matrix A, but for some other matrices which arise from solution of physical systems, there are some more I will say some methods which follow needs less number of operational steps, like a tridiagonal matrix elimination method, or using tridiagonal matrix algorithm, or using tridiagonal matrix algorithm we can do alternating direction implicit method. All these methods we will see in the subsequent classes. Thank you.